So for the next few minutes, I'm actually going to try to give you an idea of what this thing actually is, like what it guarantees. Okay. So to do this, at least at the first step, we're going to have to model this as a sequential random process, because thinking about how this deals with logs and so on, it can get a bit confusing. So basically, the random process we're going to look at is pretty simple. So basically, it's going to have a bunch of queues. I'm going to choose n to be 4 here, so just imagine four queues. And imagine that I always insert consecutive integers. So basically, I just insert the rank of the element I'm currently inserting. So basically, first, and I do this uniformly at random among the queues. So basically, I insert 1 here, 2 into 3, 3 into 3, 4 into 2, 5 into 4, and so on and so forth. This is not a very interesting game, so I'm just going to skip over it. Okay? All right. So then, whenever I remove something, I'm going to use this kind of two-choice property sort of sequentially to do it. Okay? So imagine that my two choices are, okay, and the cost I pay at a step is going to be the rank of the element I remove among all of the remaining elements. Okay? So just to give you a sort of example, imagine my two choices are 4 and 2. I remove element. Which one do I remove? 2. Everyone should know it's 2. So, hopefully we all agree. If you don't think the element is 2, then we have a problem and we should solve it now. Okay. So, all right. So the element I remove is 2. What is the cost of 2? It's 2, right? It's its rank among all the remaining elements, which is, I mean, there's 1 in there, so its rank is 2. Okay? So cost of 2 is 2. So then imagine my two choices are 4 and 5. I remove 4. The cost of 4 is 3. Yes, excellent. Okay. All right. So this is getting a bit old, so I'm going to stop here. So basically, I imagine I do 1 and 3. I remove 1. Its cost is 1. Okay. All right. So hopefully everyone understands the sequential process by now. Okay. So yeah. Any questions? All right. So then the question that we're going to try to answer is, what is the average rank removed over a sequence of steps? So basically, at a random point in time, what is the sort of the distance between this and the perfect priority queue, which always gives me the best element at each step? Okay? So this is kind of the average distance from an optimal queue, which is kind of the sequential version. Okay? So it turns out we can prove something very strong about this. So basically, what we can show is that given a set of n queues, at any time, like if you run this for infinitely many steps, at any time t, the cost at t is going to be order n in expectation and order n log n with high probability. Okay, so this is a recent paper we have in PodC. So basically, what this says is that your average rank error only depends on the number of queues that you're using, and depends linearly in the number of queues that you're using. Okay? All right? So what is our trade-off between okay, so we have n queues. What is our kind of average contention per queue? Like number of threads that sort of hit a queue on average. N threads, n queues. Average contention is like 1. So usually you just go to a queue and that's your queue, right? However, and your relaxation factor is n, is linear in the number of threads. So technically, you've managed to, you're doing much better than this crappy relax counter that we did before, because that was reducing by 2, and then it was increasing a relaxation factor by n. Right? Okay. So there are a couple of things to notice about this. So the critical thing is that the cost does not depend on t. So we're going to see that. For instance, so basically you can run this forever and it will remain stable around its kind of average point. Okay, so we're going to see why this is important when we look at counters. Okay, the other thing is that these bounds are kind of the best you could get for any type of random process that looks like that, because since it only looks at 2 queues, it can't really see it. You couldn't get better than order n average cost. Okay. The other thing which maybe some of you are wondering about is, what happens if I don't do 2 choices, and compare, get the best one, but I just do one choice. So basically, I do random insert, random remove. Okay. So that sounds like a similarly reasonable hack. Why wouldn't that work? Turns out that's like much worse. Actually, that diverges in the sense that its cost at a time t in the future, it actually depends on t, so it goes up linearly with t. So basically, the more time you run this for, the worse it gets. Okay, and this is not something that you want. You want some relaxation factor which only depends on the number of queues. Okay, so this is kind of the I mean this is one of the things the main thing I want you guys to remember. So basically, there's this kind of simple strategy which actually looks like a hack, but actually does give you pretty strong bounds. And turns out this actually performs pretty well in practice, as we're going to see a bit later. Okay, but before we go to the experiments and applications of this, I'm going to torture you for a bit with the analysis, because we spent a lot of time sort of trying to work out the proof. So I want you to suffer as well. Not really, but I think. It is really, I mean, the reason why I'm going through this is that I think it has a couple of useful tools in case you see like similar data structures. Okay, so I mean the approach, I mean the first approach one would try is basically, all right, so you have all of these random choices and you try to understand what's going on step by step. So basically at some point, step in time, you keep track of what is the distribution or what ranks are in which queues, and then you try to understand, if I remove one element now, how much worse or better does this distribution get? Okay. Turns out there's kind of something very nasty which ruins this type of strategy, which is that basically your choice at the step and basically how things evolve from step to step are very correlated. They depend a lot on what happened in previous steps. Okay. So I'm going to basically imagine we have this situation over here where basically, the queue number 1 has, this one has 1, 10, and something we don't really know on top. Then this is, it used to have 4, we removed it, 2 got removed, 5 and 9 got removed. And then we have 7 and 3 here, which are our choices for the current step. Okay? And then I'm going to challenge the Sudoku players among you to tell me what is the value of this here. What is the, I mean, what has to be here? 6, excellent. Your Sudoku fu is very strong. So basically, just to go over it in a bit slower. So basically, in this configuration, just because of the elements that have been removed and what's on top, the only element left that could match could be 6, in fact. So basically, 6 has to be here. So we're going to remove 3, and deterministically 6 has to be here. Okay? And unfortunately, this complicates the analysis like a tremendous amount, because technically, at every step, your choice could be forced here. Okay? Even though you know that the distance between 2 consecutive labels at the queue is n, the number of queues, because you're choosing uniformly at random in each step. In some steps, your choice is completely deterministic, right? So whatever type of analysis you do has to sort of get around this heavy correlation between steps, between consecutive steps. Okay, so this is why we actually need to take a very completely different approach to analyzing this process. So basically, we need to forget about this this sort of integer insertion process completely if we want to hope to analyze this. Okay, so the actual argument. So I just gave you something that doesn't work, so I'm going to try to give you something that actually, or at least a bit of a sketch for something that actually does work. So as I said, so this is sort of a short presentation of a pretty complicated argument, so I don't expect you to follow completely. I gave you the link to the paper, and I'm happy to answer questions afterwards. So basically, the actual argument will analyze a completely different process. Okay, so basically we're going to look at an exponential process where instead of inserting integer labels, we actually insert real values, like consecutive real values into the bins, where the increment at the step in a bin actually is an exponentially distributed random variable. Okay, the key observation for making this work is that the rank distribution in this exponential process will have exactly the same, so it will have exactly the same properties as the original rank distribution, okay? Then the second step, which you can find in this Potsy paper, is that we're characterizing the value distribution in this exponential process. So basically, we want to know how far do the values can get from the mean in this exponential process, and this is done by a technical gadget, which is called the potential argument. And then we characterize the rank distribution of this exponential process by because we understand its value distribution at that step, and then we're able to prove that the average rank is order n. Okay, so I think I'll skip a bit over the details of this since I want to cover a couple of more applied things in between. But the thing is, we get this. I mean, as you remember, we get this very strong rank guarantee, which is order n for where if you have n queues. So basically, you can parameterize this by the number of queues. It doesn't actually depend on the number of threads. Okay, so we can actually use this process for relaxed concurrent queues, priority queues, and counters. And I'm going to give you the queue example and counter example just now. One thing that's kind of interesting with this is that you could argue what happens if you actually do less than 2 choices on average. So imagine that I flip a coin like whenever I do a delete min, I flip a coin first, and with probability 1/2, I just remove from my own queue, and otherwise I do the 2-choice process. I pick 2 queues at random and remove from either of them. Okay. So then the question is, does this still work? I mean, basically, on average, this does 3/2 removals, 3/2 sort of random accesses instead of 2. Okay? So it turns out that if you do 2 choices only beta% of the time, then the cost becomes order n over beta squared. So basically, as beta becomes smaller, so you're going towards this uniform removal process, your rank guarantees get worse by this beta factor. Okay? So the reason why I wanted to mention this is maybe not the rank guarantee, but this works really well in practice because you can actually you can still get rank guarantees, whereas you preserve locality very strongly because on average, like most operations by a thread actually only access its own queue. Okay, so then you can also I mean we assumed completely uniform insertions, but actually if the input distribution is biased, this turns out to be still reasonable. I mean the bias cannot be too large. Okay, so let's look at a couple of experiments. So this is basically this is KLSM, which is kind of a structured relaxation. So this is a queue which does always gives you the best out sort of the max relaxation you can get from this queue is 256. So basically, the worst rank that you could get at the step is 256. This is a different data structure published by Filipas Tsigas and some of his colleagues. This is how the spray list or the Linden version. So basically, this skip list based version does. So this is the blue line here, the sort of blue dotted line, and these 3 lines are basically the first one is the version which does 2 removes. So this is red. Green, dotted green is you do 2 removes 75% of the time. Otherwise, you do a single random choice. And then half of the time, if you do half of the time 2 choices and half of the time just 1 local choice, this is the throughput that you get. So technically, you see, the less random accesses we do, the better our throughput is. Okay? So, all right. So this is, and also this is what the quality guarantees are as you change beta. So basically the smaller beta is, the worse your quality guarantee ends up being in practice. Okay? So now, all right, so let's take a step back from all of this probability and so on. So let's actually look at how you can use this trick in practice. So imagine I want to implement a queue, okay? A queue is a special case of a priority queue where priorities are timestamps. The older an element has been in the system, the higher its priority is, because we're doing FIFO, right? So our enqueues are going to sort of put a timestamp onto the element. so that we know what the priority is, and the DQ will remove an element, the element with better timestamp out of 2 random choices. Okay? So this is what the queue looks like. And then again, the theory says that the average rank removed is going to be order m, where m here is the number of queues. Okay? So technically, you can trade off contention, which is kind of number of threads over number of queues, versus the rank guarantees. So you can play with this to match the characteristics of your application. Okay? Yeah. You can we do RDTSC. So basically, Intel processors have a coherent timestamps for every thread on the socket. If you go out of socket, then you have to implement a separate timestamp mechanism. All right. So the other example is approximate timestamps. So these are basically, imagine we want to do counters now. We're back to the approximate counter problem which we had before. Okay. So imagine we have a set of m counters, for instance, 1 per thread. Okay. And then to read, imagine you just pick a random index and you read the counter corresponding to that index. Okay. Otherwise, I mean, it's totally fine to just read your local counter, but I mean, I just wanted to mention both versions. Okay. To increment, you'd need to do this kind of power of 2 choices, right? So what we're going to do is we're going to pick 2 counters at random, and we're going to increment the one that's lagging behind. So we're going to increment the smaller one. Okay. So again, this is pretty easy. So to read, you do a random choice, and you return the counter at that index times m. Okay. So then, in order to increment, you make 2 random choices, and you pick the lower counter out of the 2 random choices. So if c of j less than c of I, then you take I to be j. So basically, this I will be the sort of your the counter which has the lower value, and then you do the increment on top of this. Okay. Notice crucially that for both algorithms, I haven't added any locking, because in practice we noticed that this is not needed. And in fact, the analysis works even for the concurrent version of the process, where technically by the time you increment these values, like the relation between these values might be different, right? But this happens with low probability, so technically you can just push this into the analysis. Okay. So all right. So does this timestamp mechanism make sense? So the only sort of fancy thing we're doing here is we're sort of coupling the counters by the fact that every time you do every time you want to do an increment, you don't increment a random counter, but you increment the best out of 2, or sort of the worst out of 2 counters. Okay? So it turns out this is enough to be good enough here. So again, theory says that the average distance of from the true value that you get at a step is going to be order m, where m is the number of different counters you have. So again, if you want a structured relaxation where you can only afford some amount of relaxation, then you can trade this off. Okay. So again, you can trade off contention, which is n over m, versus the rank guarantees that this provides. So let me actually give you some empirical tests for this. This is done in Python, so technically this is only simulates the sequential process, but we also have a slightly more intricate test on real counters. The first thing I want to say is that this really scales linearly. So I couldn't get the nice graph in time for the class, but you should believe me that this scales really well. So let's look at basically how the timer distribution works. So basically, on the x-axis, I just take a lot of steps, and this is the value that I read as more and more increments are going on, right? So notice that a perfect counter would just give me a single line, which is kind of 45 degrees here, okay? However, because I have some degree of relaxation, sometimes I get smaller stuff, sometimes I get larger stuff, okay? However, what's critical here, and this is something that I really want to emphasize, is that basically these differences are nicely sort of concentrated along this 45-degree line. Right, so notice we never get something that's really, really behind or really, really above. Right, so it really is, I think, the max difference I saw over these experiments is maybe 20 or something, and this is for hundreds of thousands of steps. right? And these are 64. These are 64 different counters. Okay. So even like what the theory says is that the average distance we get is bounded by order 64, but actually the constant in front of that is actually pretty low, at least from these experiments. Okay. So this because you yeah, that's a good point. So actually because you multiply by m here. So notice that I mean I could yeah, you need to multiply by m here, and I'm not sure how I would fix this. I haven't thought about this, but I think technically you can get it to always be like, at least with very high probability, to be upper bounded by the true count. But I mean, technically you could multiply this by, if you multiply it by something, if you multiply it by something small, slightly smaller, you could get it to be bounded by up. Okay? But yeah, hopefully this answers your question. All right. Okay. All right. So the other thing is, so remember this kind of random insert remove process, the one that doesn't do two choices but does one choice. So I wanted to show you how that works. Okay? So notice we run more and more steps, and these are the values we get. And hopefully it's clear that this gets worse as we run for more steps, right? Because these are this is the kind of the choppiness of this, right? So notice, I mean, there's a clear difference here. Hopefully, I mean, this is what divergence means here, right? Basically, your distance gets larger and larger as you run for more and more steps. Okay. All right. So the last 15 minutes, I want to sort of step back and talk about something completely different. Okay. And in fact, this is sort of more of a funny story than a story about concurrency, but I think it's very useful because it sort of opens up some applications which people maybe haven't studied so much. So how many people here have taken a class in machine learning? All right, so it's good but not great. So I'll do like machine learning in one slide. Okay, so here's machine learning. So you have data. You have a task. You want to classify data. These are cats and dogs. You want to say which ones are cats, which ones are dogs. You have the task. Okay, let's say classification. You're going to have a model which encodes your belief about the data, and you're going to essentially measure the quality of that model via a loss function. Okay? So basically, you're going to have a model like a linear regression or a neural network or something like that, and that model will go over examples and classify examples. At every example, you're either doing well or not well, and the loss function will encode the notion of quality with respect to something you care about. And the critical task in machine learning is to find a model which minimizes this loss function over this data. Okay? So hopefully this makes sense. All right. So this is all the time I have for. So I have to explain this. So this is all the time I'll use. So basically, this is solved via an optimization procedure. Okay? So you can have different optimization procedures, but turns out there's this really powerful one which a lot of people use, which is called stochastic gradient descent, which we're going to talk about today. So okay, so I did machine learning in one slide. You're now all experts in machine learning. So now let's do distributed machine learning in a shorter slide. Okay, so distributed machine learning is just like a partitioned version of this. So basically you have your data set, but your data set is so large that, for instance, it doesn't fit into the memory or the disk of a single node, so you're going to have multiple nodes. Okay? Or alternatively, in the concurrent world, you want to take advantage of concurrency, so you're going to split your data set among multiple threads. Okay? And then they're going to each optimize over its own fraction of the data set. So this guy goes over this half, this guy goes over its own half, okay, of the data set. However, you want them to communicate because you want them to jointly optimize a function which is the sum of losses over each data set. Okay? So basically, there has to be this kind of critical synchronization going on between the threads, so that because they're essentially optimizing a single model based on different data. Okay? Does this make sense? All right. So as I said, there's this kind of sort of backbone or workhorse procedure for machine learning, which is used in neural networks, regression, and so on, which is called stochastic gradient descent. So basically, stochastic gradient descent is just like a fancy version of Newton's method. Okay, so basically, you see a new example at a step t. You want to update your model based on the quality of your current model at that example. Okay, so that update is basically encoded by a thing which is called a gradient at that step. Basically, this is if your error at that step is large, then your gradient will be large. If your error is small, then your gradient will be small. Eventually, you'll get to zero gradient, which means zero error, so you're going to stop. Okay, so stochastic gradient descent is kind of a randomized version of this algorithm, which only looks at one example at a time. So basically, you choose a randomly like sort of a random image, okay, and you perform this update on the model based only on a single image, as opposed to going over all images like gradient descent does. So basically, you're going to do this step, where this is just basically an approximation of the real gradient over the whole data at the step. I mean, I guess this part is, I mean, for those of you who understand it, that's good. If you don't understand it, it's not essential for the rest. Okay, but I mean, the point is that you're going to have all of these minor updates happening possibly concurrently at different steps. Okay, so and you can prove sort of standard convergence. So basically, if you run this procedure, then eventually you're going to converge to a local optimal, at least in terms of the machine learning background of this. Okay, so what does this actually look like when you implement it on a system? Okay, so you want to converge to within some error epsilon. You're going to pick a random example which has some label. Okay, so you just pick it randomly. You compute the gradient using some, I mean, this really depends on your loss function. Basically, that's the derivative, the local derivative of your loss function based on a current model, based on the example, but also and taking into account your label. So basically, the distance between the real label and the label predicted by your model is basically gives you the value of the gradient. Okay, so then the model is simply a d-dimensional vector. Okay, it just contains some numbers. So basically, in the case where I'm trying to classify these points as either green or red, the model basically encodes this plane here, or this line here, okay? So basically, every time I see a new point, if the point is misclassified, I will just update my model. I've just changed 0.5 to 0.6, 0.1 to 0, 0 is going to stay the same, and this is probably going to get a bit, go a bit different, sort of change a bit. So basically, you see new examples, and you need to update this shared vector, which is initially 0, but then sort of gets better and better at classifying your points as you see more and more examples. Okay? So does this make sense, roughly? We have just this procedure which just needs to update a vector at every step, okay? And after every step, we just compute our loss to the data, and we see whether we can stop or not, okay? So one thing I should mention is that in practice, I mean, so there's this gradient computation step, and then there's this update step of the gradient. This is kind of more expensive in terms of writing, because you have to write to all of these, like you have to write to the whole vector. So usually you just batch several examples into a single, so you just add their gradients and only then update it, okay? All right, so then, how would this work if I wanted to implement it on 2 threads? Okay, so notice that technically to simulate the sequential algorithm, I mean I can access points in parallel because they're partitioned. But then if I want to read the current value of the model and update it, then if I want to stay consistent with the sequential algorithm, then I will need to lock. Right, I need to allocate a lock for the model. After I pick the label, then I will actually need to read the whole gradient, read the current value of the model, and then compute the gradient and update it while still holding the lock, because otherwise it might become inconsistent with the actual sequential execution. Okay, so the problem here is we're going to get to pretty much the same issue that we've sort of dealt with for the whole rest of this talk, which is that we have contention on this lock. Okay, so I mean you could use a better lock, or you could sort of try to use lock-free techniques. So for instance, you could try to make this. I mean, this is practically no parallelism, right? Technically, everyone has to go through the critical section in sequential order. Okay, so then we could try to make this a bit more fine-grained in the sense that we could basically allocate one lock variable per model component, and then you just lock that one and you only update it. Okay, this is, I mean, this works. It works a bit better, but it still has a huge amount of overhead because, for instance, like for neural networks, they have like millions of parameters. So technically, you're going to have like to have a million locks for that. So it probably, I mean, this works. But it still has, for instance, the issue. So you have to allocate a lot of locks, but it also has the issue that if two threads need to access the same model variable, then they're actually going to contend on the same location, right? So you're still, even fine-grained is not going to get you very far, right? So furthermore, this assumes that these reads of the model can be inconsistent, and so can the sort of loss computations. So they have to sort of, the algorithm has to support these kind of inconsistent reads, okay? So then, so actually this has been proved to still be okay by some machine learning researchers, okay? So now comes kind of the interesting observation. So there's this story that there's this group from Stanford who was trying to optimize this. Basically doing like lock-free versions of this. So basically they were trying to do updates and compare and swap or something like that, and sort of make this somehow work better. And sometime during debugging, they actually forgot to put the locks here. They just commented them out, and they just ran it. First, they noticed two things. This starts to scale really well because there are no locks. Also, this converges. It still converges. So their algorithm, which is called Hogwild, just is exactly the same as sequential SGD, but without any locks. But run concurrently. Okay. So the interesting bit here is that first this works. The second thing is that actually you can prove that it works. So this is highly non-trivial to prove. There's probably 10 papers on proving this under various assumptions, but this works. So this is this is actually quite a big sort of a leap forward. It was a leap forward in machine learning because they were suddenly able to scale much better, right? Because they didn't have to use any locks. So there's again, as with most theoretical results, there are some issues to keep in mind. So basically, for instance, imagine that some of your updates get delayed by a long time. Technically, that delay can affect your convergence. So technically, if you have very large delays, and they can also show that you have a loss in convergence rate. So it doesn't come for free. Okay. However, okay, so by the way, Hogwild means wildly or intemperately enthusiastic or excited. So I think this is kind of a very nice nice name for an algorithm, even though it's not somewhat funny. And also, I found this personally, if you cite their paper and don't put the exclamation mark, they get really upset and they send you an email. So all right, so the algorithm is called Hogwild with an exclamation mark. So anyway, so these are some experiments from some work we did where we compared various versions. So as you can see, locking or not locking really is the difference between scaling and not scaling for these for various instances of this algorithm. So I thought this was kind of an interesting instance of relaxation because it's like total relaxation. There's no, there's practically nothing non-relaxed here. So basically, what have we learned in this class? Just to sum up. So basically, we noticed that there are these various instances of relaxation. Basically, you take these data structures and you just try to make them scale by reducing their semantics. And this allows you to reduce bottlenecks. And the key thing to keep in mind, maybe beyond these like small tricks that I showed you, is that it really matters what the application semantics are. So for instance, for SGD, they were able to like do away with synchronization almost because the application was okay with it. The algorithm was still able to converge, right? For Dijkstra's, we're able to do away with some synchronization. We do some extra redundant work, but it works. For other versions, like sometimes order matters, right? It matters whether I put my shoes on before my socks or the other way around, right? So sometimes it will work, sometimes it won't work. You need to think about sort of the implications of that. There's another last point I want to make, and this is some recent work by a group in Austria, where they essentially looked at the amount, they essentially looked at the average number of inversions. So remember this point, this philosophical point I tried to make about queues and sort of the practical assumption that actually, the fact that concurrent algorithms need to sort of provide for the case where we do inversions anyway. So these guys, what these guys did was they looked at the average number of inversions for a huge number of queue implementations. Some of them relaxed, some of them not relaxed. So basically, these are some of these are like the Michael Scott queue is in here. For instance, this is this green line here, okay, and the two random choice queue is this thing over here. So this is basically the distance. Like this is the average inversion rate between when the tasks are actually performed in a queue implementation. Okay, so what is kind of surprising here is that with some relaxed data structures, you can actually get much fewer inversions than with like for instance with the Michael Scott queue. And the reason why this is, at least just by trying to understand the results and repeating them, is that because these like queues which scale worse have much higher variance in their running time. So technically, the point where you actually get to execute the task might be very far from the point where you removed it, where you started to remove it. So technically, in practice, it might not matter so much that you're relaxing. So it seems like, at least for some applications, it seems way more important for your data structure to scale than to actually provide you with perfect linearizability guarantees. At the same time, I want to stress out this point, which is like 3,000 level of inversion. This is actually the one random access. So this is like a random insert, random remove. So you have to do this in a somehow structured way. You can't just randomly relax your data structure, because you can get like this is 3,000 inversions on average. This is 66. This is 22. So it really does matter. You really need some kind of structure to your relaxation. You can't just do this hog wild, as they say. Sorry? The first one is flat combining, which has practically no inversions because they're performed sequentially. Okay? All right. So the last slide of my talk, I just want to sum everything we've seen so far. So the first idea that I want to leave you with is that there are some data structures which are going to be hard to scale if we think about them sequentially. Okay? The second point is that many of the data structures we sort of grew up with, like queues and priority queues, have to change because they're hard to scale. So we're getting sort of funky versions of them, whether relaxed, whether sort of weaker progress semantics or something like that. So basically there's a lot of activity in this area. So then two instances that of relaxation that I gave you were relaxed semantics and optimistic progress guarantees. Then I think there are kind of very interesting open questions related to this. So basically, how do you exactly specify what's going on with this data structure? How do you relate it to something that people can understand and work with more easily? And then how do they interact with applications? This is still not exactly clear. And then the thing that excites me most is that there seems to be space for new data structures. So basically, you just come up with a completely different idea, and it's kind of an instance of, it can be an instance of something really new and exciting. So thanks for your attention, and I'm happy to take any further questions. Yeah, sorry, so this is not convergence, this is scalability, right? Yeah, so basically this is the percentage of non-zeros. So basically this is the sparsity of the model. So in some applications the model is very sparse, like support vector machines have very sparse models. So this would be towards here. And some other applications would be like they have their very dense models. So processors would need to do a lot more updates. So this is sort of the difference here. Okay. Yeah. So the difference. Okay. So does everyone understand the question, or should I repeat it? So I think in brief the question was, what's the difference? Why is there this qualitative difference between one choice and two choice? Okay. So and your first example was that of a billion queues. But okay, so the two choice process for a billion queues will tell you that your maximum, like your average inversion will be order of a billion. So, I mean, if you're happy with that, then I mean, it is true. It will stay order of a billion. It will always be order of a billion. But it doesn't give you something very strong, right? It's pretty weak. So the approximation factor depends on number of queues, right? Yeah. Why? So it's yeah. I think that's a fair point. So maybe I should. It's a very good point, actually. So let me try to get back to this. So basically, if we look locally, so this is the one choice algorithm, okay? If we look initially, like on individual steps, initially this does not do very badly. It's just that over time, these queues become completely desynchronized because the counters in this case, they become completely decoupled because they're not connected in any way, right? There's no coupling between them, right? It's just like it's a completely random process. Right? You could think of them completely independently. There's no reason they should be correlated in any way. And in fact, this is why you see this. Whereas here, there's this extra coupling which keeps them. I mean, it has the same behavior locally initially. I mean, this is not any better, but it just stays the same. Okay. So it's just that there's this extra kind of noise which accumulates in this case, but which is bounded in this case. Okay, so locally there's not anything much better that it's doing, but globally it's fine. Let me try to give you another slightly different explanation for this coming from the analysis. So basically, the main difference between the two-choice process and the one-choice process from the analytic point of view is that the two-choice process prefers to get better elements. So basically, the one-choice process just gets an element. You want an element, I give you an element. The two-choice process does two choices. So basically, the probability that it gives you a better element is slightly better than random. It's not much better, but it's just consistently slightly better. So it prefers to get it. Basically, the probability of giving you the best element is 2 over n, whereas the probability that it gives you the worst element is 1 over n squared. So that's a pretty big difference between the worst and the best, whereas the other one has uniform probability for all of them. You see? Okay. All right. Yeah. decreases, I think, logarithmically in the number of choices, at least for small d. So for a small number of choices. So I guess another way to phrase it, it doesn't get much better. Like a 3 is not much better than 2, 4 is not much better than 3. So I think it decreases logarithmically in the number of choices. So you'd have to have a lot of choices to see a real difference. Yeah, you get like every extra choice costs you an extra cache miss on the fast path. So it's not. I mean, yeah. So I don't know. It depends on the application, right? There's this trade-off. It depends where you are, where you want to be. Yeah. So it's not clear if it's worth it. Sometimes it is. Sometimes it's not. Yeah. 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 1Q. Yeah. Yeah. Yeah, okay. So there's a bug in this formula because it doesn't provide, so there should be like for beta greater than 0. Because technically, I mean, this is not exactly wrong, but it doesn't make sense. So technically, if beta is 0, then this is infinity. Yeah. Yes, if it's really, really small, it won't diverge. But it's again, the thing is like, are you happy with the relaxation factor of 1 billion? You see? Yes, yeah. So it could be really, really small, but it won't diverge. I mean, I'm not sure. So actually, the analysis for this assumes some lower bound on beta, so it can't be like arbitrarily small. Um, well, actually, no, that's not true. So yes, actually, this version assumes it. But so it will work for any fixed beta. It gets like you need to square it and multiply it by a number of q's to see what your relaxation factor is. So it might be meaningless after some point. Yeah. I mean, I think it really is a bit like apples and oranges, right? Because like this does not tell you anything about the degree of relaxation. This just tells you how many inserts and how many deletes you can do per second, right? And then this tells you what the relaxation is. But somehow, I mean, like, somehow these are not coupled in any way, right? So I could take beta to be 0 here. I would be getting a very nice graph. I wouldn't like this would probably be like very scale very well. Okay, right? But technically, you would have no notion of how close this is to like any kind of relaxation bound, right? This graph doesn't tell you anything about relaxation. It only tells you scalability, right? This is why I always try to show it in conjunction with this graph so that people can see that, well, of course, the smaller the beta, the better you're doing, but actually the smaller the beta, like the worse you're doing in terms of rank, right? So there's a trade-off. Ultimately, in practice, what drives this what drives this is in your application, both things are going to matter. So if you think about it, you have this extra time. Like, imagine you're implementing Dijkstra's algorithm. So basically, the more relaxed you are, the more often you will need to look at the node again, right? But you're going to be faster in removing the node. But these are kind of two decoupled things, right? So the application kind of couples them. Okay. Yep. Hmm. So for data structures, I'm maybe less aware. So basically, the question is whether you can do like a deterministic stochastic schedule or something like that. I mean that. Yeah, so like a deterministic but not worst case schedule. So I think, so for data structures, I'm not aware of this work, but I think for distributed systems, there's this notion of, for instance, a failure detector. So basically, this gives you a restriction on the set of interleavings that you can have, right? Basically, for instance, every process has to take a step every 1,000 operations. That you can't starve a guy 4 steps or something. So I think Piotr's actually research recently has looked into kind of adversaries and how they interact with what you can solve, but more at a more theoretical level. Yeah. So I think unfortunately, just to conclude, I think unfortunately what's going on is that you can get very bad schedules even if you restrict the adversary like locally. So it seems like you need this extra